Gorenstein and rational of dimension 2 means rational double point. This is easy. So 2-dimensional Gorenstein rational singularity, rational, but one can show that for a general point Q in V. So this point is P, but suppose I have a general point Q. So this is an observation I learned from Professor Miles Reed's paper, that for a general point Q in C, V is analytically a product of, let's say, P cross disk, where P is a germ of a rational double point and delta is a one-dimensional disk. So analytically product just means it is kind of cylinder cross some lower dimensional thing. So in this case, because of assumption of rationality and Gorenstein-ness, you have a rational double point cross disk. But you can easily see that this, if this rational double point is actually not smooth, then the local fundamental group of this is non-trivial. So if Q is singular, then local fundamental group of V is not trivial, because the rational double point, if you remove the singular point from the rational double point, you get a non-trivial fundamental group, and then cross the one-dimensional disk. So local fundamental group is non-trivial. But suppose I have proved further that the fundamental group of V is an upper semi-continuous function, and at this point I have assumed that at this point the local fundamental group is trivial, and suppose I have proved that the local fundamental group is upper semi-continuous, then at nearby points also it has to be trivial. But if there is a genuine singular curve, then the local fundamental group by this observation is not trivial. So this is how you prove that finally you prove that some variety will have isolated singularity. And that is essentially, that is, I am saying that the singular locus is in codimension 3. This is how the Popov's conjecture is proved. So now reduction to phi 1 P V equal to 1. So now I am continuing with the proof. So I have the situation f from, let's say, WQ to VP. Since the problem is purely local, I can assume that I have a map of germs such that this has here what is assumed is that this is locally simply connected, so this is trivial, and Q has isolated singularity. And this is a finite map, and I want to prove that the local fundamental group here is upper semi-continuous. So suppose so if phi 1 P V is not trivial, we know that this group is finite because this group is trivial. So suppose this is not trivial, then by the remark about the quasi-universal cover, you get a factorization, let's say T something Q1 to Vp, where this is now locally simply connected, and then so where phi 1 Q1 of T is trivial, and this map is non-trivial. So the problem from this is reduced to this case where the degree is smaller. So then, assuming the induction, I have proved the result for this, namely this has isolated singularity. But now there is an additional information we have, namely because this is quasi-universal cover, there is a group acting on this. Whenever there is a finite group acting on this, the problem which I have stated is easy to prove. Suppose I have a locally locally simply connected thing above and with a finite group, then take the quotient. Then the quotient has upper semi-continuous fundamental group, this is easy to prove when in the presence of a finite group. So by this trick, you can assume that, so we can assume that we have reduced this case. So this is essentially an exercise that suppose I have a locally simply connected space and finite group acting, take the quotient, then the local fundamental group of the quotient is upper semi-continuous. This is a very easy, it's essentially again covering space theory. Can assume that phi 1 p v is I want to prove now that under this assumption, I want to prove, we want to show that phi 1, let's say now I'll change the notation. I will the local pi 1 of v at points near to p is trivial, because once this group is trivial, upper semi-continuity means that for nearby points it is also trivial. But now remember, I have used some assumption in the bracket, namely w is factorial. Right now let me continue with this hypothesis. So once w is factorial and I have a finite map, it is known that the divisor class group of v is finite by some easy argument. But if further the local fundamental group is trivial, then factoriality of this implies this is also factorial. So then v O v p is also factorial. Further, we have assumed that w has isolated singularity. So w minus q is smooth, and there is a finite map from w minus q v minus p, because this is map of germs. So q is the only point lying over p. So I have a finite map of this is a smooth manifold because w minus q is smooth. So this implies that v has isolated singularities. V has rational singularities. Outside P. But V is also, see, once V is factorial, in any factorial variety which is Cohn-Macaulay is Gorenstein. So is also V is also Gorenstein. So what do we know about the singularities of V minus P? They are both rational and they are Gorenstein. So they are all rational double points. So hence V minus P has at most rational double point singularities. So in fact, we want to show that there are no such singularities, because I want to prove that the local fundamental group of V is upper semi-continuous. So outside V minus P also is locally simply connected. And I have already indicated an argument that if you have rational double points, a whole curve, then the local fundamental group is not trivial. So I want to prove that these other singular points don't exist. So we have the situation W, Q, and here is V with P, finite map. So let H be a general hyperplane passing through P. So you can think of some general hyperplane passing through P, and because I have assumed that, now remember V is factorial, I have reduced to the case that V is the both factorial and locally simply connected at this point. So general hyperplane will be, so then H is a prime element in the local ring, but it is also prime element here. H is also a prime element in OWQ. This is some kind of local Bertin theorem of Flener, that because this map is finite, so if I take a general hyperplane here and look at it above, then this hyperplane is also a prime element here. So let me draw, so call it here, let's H defined by small h equal to 0 and its inverse image here H prime. So this is the notation, and so assume that the singular locus is a curve C. Then I have already indicated, if this happens, then the local fundamental group is not going to be trivial. So I want to produce a contradiction. I want to prove that essentially I want to prove that the singular locus of V is a point. So suppose it is a curve. So let's draw some kind of singular locus here, C, and so now so here is some technical lemma or something. I will not prove it, but can assume that phi 1 of W minus H prime union C prime. So inverse image of C I will denote by C prime here. So suppose can assume that this 2 pi 1 of V minus H union C is onto. So this looks somewhat technical, and it is somewhat technical. The reason I need it for for some later step. So if this was not surjective, then you can go to some another factorization. So because of non-surject, the image of this has finite index. I already stated a lemma. So you can factor this map into some, and then one has an induction hypothesis. Basically, once you have induction, then you prove the result here, and then so because of that induction purpose, we can assume that this is surjective. Now the importance of this will be clear only later, I think. So again, just for simplicity, assume that C is irreducible. So of course we are talking about germ, so C is an analytically irreducible curve, and what we know is that, so we know that we have phi 1 of V minus C is trivial, because this is just the local pi 1. If you remember, the local pi 1 of V was defined by taking a small neighborhood of P, which is V because V is a germ, and removing the singular locus because C is the singular locus. So this is just the assumption that this is equal to 0. Okay. So assume that, so first consider the case when C is smooth. So I have a smooth curve as a smooth curve as the singular locus. So then H, see if you remember the H was the general hyperplane. So H restricted to C is the uniformizing parameter. For C at P, because the local ring of C at this point is DVR, so general hyperplane will be the uniform. So then it follows that all the small translates, so all the translates like H equal to C, so you get basically, so this gives a fiber bundle from, if I take a suitable neighborhood, so I take a neighborhood of C, small neighborhood, let's call this neighborhood N. So from the boundary of the neighborhood to C, because all the translates of H now, because C is smooth, all the translates will be homeomorphic, and from the boundary of the tubular neighborhood to this is a fiber bundle. So this implies that, but what is the phi 1 of the boundary is same as phi 1 of n minus C. N minus C deforms, the boundary is a strong deformation factor of n minus C. But this is assumed to be trivial because the local fundamental group is trivial. So the boundary is trivial. But because this is a fiber bundle and C is a germ, so C is like a small disk. So this bundle is trivial. That means, so this implies that even the hyperplane, it follows that this implies that H has no singularity at P, because when I take H equal to C and its intersection with the boundary, since the boundary is simply connected, it follows, and because C is like a disk, it shows that the fibers are all two spheres. In particular, this intersection H equal to 0, it intersects this neighborhood in a two sphere, which will mean that H cannot have a singular point at P. But this is a contradiction because V was singular, so this is a contradiction. Since P is a singular point of V. So once you have a singular point of a variety, if I take a hyperplane section, it is still singular. But assuming that the singular locus is smooth, we get a contradiction. So that shows that this C shouldn't be there. So in the case, special case, where C is smooth, we have proved that there is no C. Actually, singular locus is isolated. So now we have to reduce to this case by some ramified covering trick. So suppose C is singular at P with multiplicity E. So then H restricted to T is T raised to E, where T is the uniform, T is a because locally analytically in one complex variable, every holomorphic function is power of some uniformizing parameter. So there is a parameter like this where H restricts to. So now what I do is I take, so I join H raised to 1 over E to V and W. So I get some ramified cover. So we get V prime and W prime and a finite analytic map f dash from V prime to W prime, because I adjoin the same root for both the local both the local rings, and I get some here W prime. But what is the property of this map? This map is ramified only on h equal to 0, because I have taken the eth root of h, so only on this. So outside this, the map is still unramified. That means, since if V has a singular locus which is a curve, there will be still a singular locus here which is a curve. But then some analysis of that technical thing which I stated, using that you can reduce this situation to this situation, where the local fundamental group here is trivial. This has isolated singularity because upstairs, remember, here, this has isolated singularity. Then I have this general hyperplane. The general hyperplane will also have isolated singularity at this point, because there is no other singular point. So when I take ramified cover of this has isolated singularity. So what you have to prove is that the hypothesis here, namely this is locally simply connected, is true here. So that is where that technical thing is needed. So then basically from here you have the situation here, where all the hypothesis here is satisfied. Then you prove that so here, so what is the final step? Let's see. So the reason for doing all this was C was singular. So, but when I take this eth root and adjoin here, the singular locus will have one irreducible component which becomes smooth, because here this h was t raised to e. So adjoining eth root of h here, basically there will be some irreducible component of the singular locus here which is smooth. For this case I have already proved the theorem. So here, because of that special case, here there are isolated singularities. But this is a contradiction, because as I said, this map is unramified outside this h equal to 0. So the curve singularity will here lift to some curve singularity. But here, because of that special case, the singular locus of V prime is isolated. So this is a contradiction, finally. So I mean, this is just the idea of the proof. Now I want to quickly indicate how Popov's conjecture follows from this, because we have to use the hypothesis in Popov's conjecture, namely all fibers are of same dimension. So, application to Popov. So here is Cn, and we had Cn mod G, the map was, and pi has equidimensional fibers. So now suppose here we have the origin lying over the vertex here. So here I take a general hyperplane, general linear space. So let L be a general linear space in Cn passing through the origin. So this is the origin here. So then it's easy to see, because so here I'm now going to use that all the fibers are of same dimension. So if I take a general hyperplane passing through of same dimension as V. So I have this general hyperplane which has same dimension. Then pi restricted to L to V is finite at origin. I mean, I am not claiming that the whole map from L to V is finite. That will be too much because this is too global. Just taking general linear space, you can't. It's not easy to make the whole map proper. But at this particular point, germ level, the map from L to V is finite. But L is smooth. Now L, and then of course L is smooth and factorial and locally simply connected. So by my theorem, the local fundamental group of this is upper semi-continuous. But it is okay. But so the final observation is that so suppose this vertex is P. So then it is easy to see that pi 1 P of V is actually trivial because all the fibers are of same dimension. So if you take L, for example, from L to Cn, no, I'm sorry. The argument is because Cn to pi inverse of singular locus V to V minus singular locus has connected fibers. Because fibers, the fibers of this map are connected. So this map has connected fibers, but this is simply connected. The main point is this is simply connected because the general fiber has all the fibers of same dimension. So general fiber, when I take this intersection here, this has codimension bigger equals 2 inside this. That's easy to check. So if I remove something of codimension at least 2 from Cn, this is simply connected and fibers are connected, so this is simply connected. So this implies that pi 1 V minus. But now we come to this finite map. I have a finite map where this is smooth, and then the local fundamental group here is upper semi-continuous, but then I indicated that assume for simplicity that dimension V is 3. Then if there was a curve of a singularity, then local fundamental group is not upper semi-continuous because at a general point on that curve, it is local fundamental group is not trivial. So finally, this is the reason why codimension of the singular locus of V has at least 3. If it is 2, then so for example, if V is 3-dimensional and singular locus is a curve, we have a contradiction. So in general, similar thing. So I think I will stop here. Stop. So if you have a let's say 3-dimensional variety whose singular locus is a curve, such that the general hyperplane section is a rational double point, then at a general point on that curve, the variety is an analytical product. This is an observation from Professor Reed's paper that rational double points do not have moduli.
General, what's the exact statement about?
No, I needed all that hypothesis because I finally had the rational singularities, Gorenstein, which
only
means
for rational double points you make that statement. Yeah. If you have a family of rational double points, then it's analytically right.
The general point, it is analytic product. No. I have sent it for publication. I'm sorry?
Your work is finished, is published, or this work?
No, it is sent for publication. I have sent it.
Okay. Thank you.